Okay guys, so now let's work out the solution to this problem. So we talked about a spherical uniform charge distribution. Sigma is the charge per unit area. 2 points, one is outside, one is inside, and we have to find the potential for these 2 points. So let's call this as problem A and problem B. So let's get started. So let's start with problem A. Right? So first let's start with basic definition. So what is the definition? So V at any particular point, right? V is what? V is integral, negative of integral E dot dr, right? Where R goes from infinity to whichever point you're talking about. Okay. So now let's take the first point, which is now my x here. So as always, what I'll do is I'll take a charge at infinity and I'll bring it from infinity to x and I'll bring it along the same straight line, right? So here if I take this point, so now when I say dr, so let's say this was my distance r, then dr would be a small increase in r, right? This r is a distance here in this integral. R is the distance from the center of this charge. By the way, you might be wondering, right? The field here, why are we taking the distance from here? Should we not look at the field because of each of the charges here? Right? Now the thing is, the field here we have calculated in the previous example using Gauss's law. We showed that the field here would be exactly the same as if all this charge was at the center. If all this charge was at the center, then whatever field you would find, it's the same field here even if it's a spherical shell. So that result I'm going to use from the example of from the Gauss's law. Okay, so now my E and dr would have the same direction. So this would be direction of E and this would be direction of dr as well, right? Dr vector, right, would be, so if this is r, this is dr, right? Now this is r. In this particular case, the distance x, but I'm taking it, I take a random point. So if it's r, this is going to be dr. Right? So now these two are E and dr have the same direction. So this would be, what is E dot dr? E dot dr would be E into dr into cos of angle between them, in this case cos of 0, which is E dot dr, and therefore my V will become nothing but minus integral E dot dr, and where r will go from infinity to x, infinity to x, and therefore now I can say that my V at x, right? V at x is going to be, they have not written x, it's the same thing, right? So I mean this is my V at point x is going to be, and what is E? E will be nothing but the total charge, right? The total charge minus infinity to x. So if the whole charge was here at this point, let's say this whole charge was q, right? Let's say this whole charge was q, right? Q. Then this would be kq upon r square into dr. Sorry, this capital Q, so let me be careful, let me just use consistent notation, this capital Q, right? This is my capital Q. Okay, so now k and q are constant, let's get it out. So this would be minus kq, sorry, capital Q kq into, let me just write this neatly here, minus k is equal to minus kq, right? And this would be integral 1 upon r square dr, and this goes from infinity to x, and that would be nothing but minus kq, okay? And this would be minus 1 upon r. Again, we've done this. This would be, the integral is going to be minus 1 upon r from infinity to x, right? And what would this be? Just evaluate this. So this would be v at x is going to be equal to, and I can take this minus sign out. This minus will cancel. This will be 1 upon x minus 1 upon infinity. This would be kq into 1 upon x minus 1 upon infinity. And what is 1 upon infinity? That is 0. So it's nothing but, so I get V at x is equal to kq upon x. And what is my q? Q is the total charge, but we have been given sigma. Sigma is the charge upon unit area. What is the area? Area is 4 pi. This is r. Area is 4 pi r square. So charge would be sigma into area, right? So my q is going to be equal to sigma into area of the sphere, which would be 4 pi capital R square. Very simple. right? So same thing. So now my V at x is going to be equal to K into sigma into 4 pi capital R square, right, upon x. This is the answer. Now, what about the second case? Right? What about the point R0? Right? Now, the potential at point R0 would be same as the potential at this point. Right? If I just use the same line, because the potential is going to be same, it doesn't matter whether I take a charge and bring it to this point or this point, since all symmetric. The charge is symmetric, so this point, all the points here are, if I take this point here, another point same distance, another point same distance, all of them are symmetrically placed. So potential here is same as potential here, so this potential I can take as same as potential here. So I can use the same logic here, right, along the same line. So here I'll say, this is my case B, here I'll say V at R0 would be equal to minus integral E dot dr, where now this infinity to R0, right. So now I'm saying the work done from infinity to R0, okay. Now what would this be? So I can break down this, this integral down in two parts. So one is from infinity to capital R is here, remember this capital R, and then capital R to R0, right. So we can say that V at R0 would be equal to minus integral E dot dr, right, from infinity to capital R minus, I'll write this below this here, minus integral E dot dr, sorry, this is a vector, E dot dr, right, from R to R0. Now what is E dot dr? Again same logic, E and dr, same direction, the cos of angle between them is 1, so this would be nothing but E into dr, right. So the first term would be, so we'd say V at R0, the first term would be minus integral E dot dr from infinity to capital R minus integral E dot dr, right, from, and this would be from R to R0, to R0, right, R to R0. Now here's the question, what is E inside this? From our discussion of Gauss's law, when we found the electric field, we said that we found the electric field inside the shell is 0, right, inside the shell the electric field is 0. So this E is actually going to be 0, right, this is 0, and therefore this whole term is going to become 0. So what is left is only this term, and this is exactly the same as this, except my x becomes R, so I'll have the same result now. So just this is exactly the same thing, except my x is now capital R. Instead of x, now it is capital R. So I can say that my V at R0 would be equal to the same result, but I substitute for x, I'll write capital R, right. So this would be K sigma 4 pi R square divided by capital R, and now cancel this one part of R, and now we get this result, which is V at R0, this is equal to K into 4 pi K into sigma into capital R. This is the potential at this particular point. So just make sure that you understand each of the steps involved, because this is the fundamental, and we'll be building on this as we move forward.